Yes.
So I hope it's clear. Okay. And what about reaction with active metals? Yeah, tell me. Suppose if you react alcohol with sodium, what is going to happen? What you can see over here? That is liberation of, yeah, liberation of H2 gas. And up to some extent, this can be used to detect alcohol versus ether, differentiate between alcohols and ethers. Okay. So how you are going to make out whether the given formula is an alcohol or ether, because both have same formula. Suppose if you have C2H5OH, right? C2H6O, and one is ether, another is alcohol. How you are going to make it differentiate between them? Because both are actually functional isomers. Okay. Yeah. So tell me.
Ethers will not liberate hydrogen.
Yeah, ethers do not have that acidic hydrogen, so they will not liberate acidic hydrogen, right? And what about alcohols?
They will liberate hydrogen.
Yeah, they will liberate H2. But this is up to some extent you can differentiate between alcohol. But if there are two alcohol, you can't use this. Why? You can't use this test if you have two alcohols. Why? Because if you have two alcohols, both are going to liberate H2 gas, right? And if both are going to liberate H2 gas, then how you are going to make out which one is which alcohol is which one, right? Both the alcohol are going to react. So one, it can be used to distinguish only alcohol and ethers, not between two alcohols. And if you have two different alcohols, what test you are going to use? Tell me. If you have two alcohols, two or three primary, secondary, tertiary alcohol, we have seen. Yeah, remember it. Very, very important. That was which test? That was Lucas test, right? And you notice the time for the turbidity.
Yes, sir.
And for tertiary alcohol, it is going to appear instantly. And for secondary alcohol, it is going to take 5 to 10 minutes. And for the primary alcohol, it is going to take half an hour, right? And now the most important reaction is acid catalyzed dehydration of alcohols. Okay. So what do you mean by this? What you know, you can quickly tell me. And then we can discuss more. Yeah. Acid, yeah, tell me.
Water is removed from alcohol.
Yeah, water is removed from an alcohol, and what is the reagent?
Alkene.
Yeah, you take, yeah,
Concentrated H2SO4.
yeah, concentrated H2SO4, yeah. Actually, you may take Al2O3 also. Okay. So that also can liberate water. That also can remove water from alcohols. Okay, and what is the temperature? Actually, for ethanol, you need to remember the temperature. It's there. It's asked many times in all the examination, right from CBSE boards to your NEET, JEE Main, JEE Advanced. That very important. Okay, so it is 170 degrees for ethanol, but for higher alcohol, it's not going to remain same. It's going to come down. Is it clear? Why it's going to come down, and what's the mechanism? Yeah. Yeah, what's the mechanism? So actually, yeah, it proceed via carbocation mechanism, right? The OH get protonated by H2SO4. You can look over here. I've taken this example, cyclohexanol. So the OH get protonated, it becomes water, okay, and it comes out as water, leaving behind a carbocation. That carbocation, because you have taken high temperature, this HSO4 minus or H2O is going to remove the H plus. That's why it is called acid catalyzed dehydration of alcohol, right? And these double bond are going to come and form these electron from the H are going to come and join with the cation, and they're going to form an alkene. Okay, this is how it happens. It needs higher temperature heat. Okay, then only the elimination is going to happen. And this is the major step. This is slow step. This is RDS. Okay, clear? So if you have a stable carbocation, a cation which can form very easily, the dehydration is going to become very fast, right? For ethanol, you can see the temperature. For 170, you will have elimination. This elimination is known as E1 elimination. Okay, clear? And if you take the lower temperature of 140 degrees, actually this is SN1. The water gets removed, but not from one molecule, from two molecules. So for elimination, for the formation of alkene, you require a higher temperature. And if you take further lower temperature, you are going to get HSO4, ethyl hydrogen sulfate. Okay. You can use one more reagent for dehydration of alcohol, and that is Al2. Okay, Al2. Yeah, Hanifa, good evening. Can you hear my voice? Al23. So we were talking
Yes.
about the, yeah, okay. So we were talking about the dehydration of alcohol. You can use concentrated H2SO4 and Al2O3 also. Okay, alumina. Concentrated H2SO4 actually gives H plus to the OH. The water it becomes OH2 plus, and it comes out as water, which is a good living group, right? And a cation is left behind, and the cation actually the H plus is removed from the position adjacent to the cation, that gives us alkene. Al2O3 also gives you an alkene, that is also an elimination reaction, right? So but you need to remember the temperature for Al2O3. Also you can have the two conditions. For higher temperature you are going to get here the alkene, because the elimination actually this requires higher temperature because the pi bond is weaker, so we need to give some energy to make the alkene. Okay, but if you have a tertiary alcohol, that is going to become that is going to react very easily, undergo dehydration very easily. Yeah, so let's do this question. Yeah, so what's going to be the answer to this one? Samaira, Hanifa. Yeah, so these questions are very common, just to have actually they try to put one more hurdle by giving you the names. Instead of giving you the structure, they try to give you the names. Okay, and they ask the names of the product. So what's going to be the answer, Samaira, Hanifa? Tell me. So 3,3-dimethyl butane to all. Okay, and what's going to happen if you heat it with concentrated H2SO4? Which alkene you are going to get? Yeah, Hanifa, Samaira, tell me quickly. So the OH is going to get protonated, right? And it is going to come out plus H plus minus H2. It is going to come out as water. Cation is going to. Okay. Remember one thing which is very, very important. The cation, always check for the rearrangement of cation. Always check the possibilities of rearrangement. And if the rearrangement is possible, you can do that rearrangement. Cation actually try to become more stable by shifting onto the adjacent carbon atom. So here you can see, I will draw the large structure. This is secondary cation. Okay. And if the cation comes here, it will become more stable, right? Because it is going to become tertiary. But here you already have 4 bonds and 3 methyl groups connected to this position. So how you are going to bring cation over here? You need to shift one group, and which group is going to get shifted? The methyl group. Okay, because you have only methyl group, 3 methyl groups. So one methyl is going to get shifted, right? So on this carbon, you will have one methyl is going to come over here, and you are going to end up with a tertiary cation. Okay. Is it clear? So this is one thing. Always check for rearrangement. Okay. And now you are going to make an alkene. This is the second thing. And how you are going to make, so this is the cation I'm going to write over here. So you can remove H either from this side or from this side or from this side. Actually, this one left and this one are same. So I will take only any one of them. Okay, this one and this one, right? Is it clear?
Yes, sir.
So which is going to be the major product? Tell me. The upper one or the lower one? Yeah, there is a rule just like addition of HBr. There was a rule which governed the addition of HBr. Okay. And there is a rule which governed the formation of an alkene. Clear? What that rule was? Hanifa and Samara, can you tell me?
Marconi formula.
No, that was for the addition of HBr. For dehydration, for removal of HBr, for alkene formation, what was the rule?
Anti-Marconi formula.
No, that was also for the addition of HBr. HBr, it is going to add in a simple way, it is Markovnikov. And if it is going to add in the presence of peroxide, it is anti-Markovnikov addition. Okay. So what about this one? So this is the alkene which we have is Setzef and Hoffman alkene. Okay, so which is Setzef alkene? Tell me.
The second one.
Yeah. So what makes us decide whether it is Setzef or not?
More substituted alkene.
most substituted, most branch. Yeah. So you need to highlight the carbon atom, Hanifa and Samira, and check how many alkyl groups are there. 1, 2, 3, and 4. 4 alkyl groups are there, right? So it is tetra substituted. Highlight the carbon atom. You have one alkyl group, another alkyl group, only 2 alkyl groups are there. So di-substituted. So more substituted alkene is going to be the major product. Is it clear?
Yes, sir.
So ZZF alkene is more stable, and that is going to be the most stable one. Is it clear? So you are always going to keep in mind that you are going to make a ZZF alkene, which is the most stable alkene, which is more in most of the cases, it is the most branch alkene. But in some of the cases, it can be less branch also. Suppose if the pH is there, you need to give priority to the pH side where the phenyl group is there, because that is going to make an alkene more stable by resonance. Is it clear? So answer is going to be 2,3-dimethyl butene. That's going to be the answer. So I hope you understood it, right?
Yes, sir.
So just we can add one more question, whatever I was talking about. So, yeah, what alkene we are going to get over here? Yeah. So first of all, you are going to remove the OH group. That's for sure. You are going to protonate it and remove it as a water OH2. You will have a cation. And this cation, you are going to bring it closer to the benzene. Okay? Because that one is resonance stabilized. So pH and now you are going to do the removal of the H plus adjacent to the cation, and that's how you are going to get an alkene. And this alkene is very stable. It is branched as well as it is having the stabilization of the benzene ring. Yes.
Yes, sir.
So I hope that is clear. Yeah. So, so let's move on to the next problem. Next reaction which we have to do is oxidation. So tell me what you know about the oxidation reactant. Yeah, oxidation of alcohol. What you get? When you oxidize alcohols?
We get aldehyde, carboxylic acid, and ketone.
Yeah, that is for primary alcohols. Okay. And when you get an aldehyde, when you get a carboxylic acid, Actually, suppose if this is a primary alcohol, you need to be very careful. If you take mild oxidizing agent, clear? Mild oxidation, then you are going to get an aldehyde. But in case if you go for strong oxidizing agent, like KMNO4, H plus heat, or K2CR2O7 H plus heat, you're going to get a carboxylic acid. Actually, what happens is they also proceed via aldehyde. The aldehyde get oxidized to carboxylic acid. If you take it, the oxidation doesn't stop at aldehyde, it goes directly up to carboxylic acid. So directly we don't get carboxylic acid, actually you get aldehyde, but if you have mild, that's it. But if you are strong, you will go up to carboxylic acid. So you need to be very careful. So you need to choose your oxidizing agents very carefully. So what are mild oxidizing agents? Tell me. Samara, Hanifa.
KMNO4, K2CR2O7.
No, those are not mild oxidizing agents. The mild oxidizing agent is actually PCC.
Oh yes, and PDC.
Yeah, PDC. Okay. And what's the full form of PCC and PDC? It is pyridinium chlorochromate. Okay. And we are actually so much used to the abbreviated name that sometimes we forget what's the structure is, and in the question we, though in spite of being aware actually, but we are not able to do it, because what they do, they give you the structure, and you, if you can't recognize that actually will we will have difficulty in solving the problem. Okay, so this is chlorochromate and this is pyridinium. Okay, similarly that is pyridinium dichromate, Cr2O7 2 minus, right? That is oxidation. Okay, these are mild oxidizing agent. Clear?
Yes, sir.
And you don't have to, you should use actually the solvent CH2Cl2. This is the solvent for dissolving. Okay, that actually that is responsible for the mild oxidation. There is another very important and given in your NCRT, that is copper's red hot tube. This is the most common one. Very, very common. Copper red hot tube. When an alcohol is passed through copper red hot tube, it get oxidized. Okay. So that's very common mild oxidizing agent. Okay. Clear? So PCC, PDC, and copper 300-degree copper red hot tube. That is very important. But you need to be very careful only for the primary alcohols. That's it. Not for secondary alcohol. So if you have a secondary alcohol, what you are going to get? If you oxidize it. Yeah.
We get keto and
Yeah, we get ketone. Why we can't get acids? Because ketones actually do not get oxidized easily. further oxidation of ketones is difficult. Okay, this is useful in the upcoming chapter of aldehydes and ketones also. Actually, when you take primary alcohol, CH2OH, you end up with an aldehyde. Okay, and these aldehydes actually have this hydrogen. Okay, this is the main cause why the aldehydes can get oxidized very easily. Okay, this can get oxidized. RC double bond O and OH. But suppose if you have a ketone, you have no OH, no H directly connected to CO. So that is the problem why the ketones can't be oxidized, and that actually um, makes our work very easy, that we don't have to be careful about the strong or mild oxidizing agent, because any one of you take, you will end up with ketone only. Clear?
Yes, sir.
So that's very important. So, and what about tertiary alcohol? Hanifa, Samaira? What about tertiary alcohol? Just give me a second, right? Yeah. So what do we say regarding the oxidation of tertiary alcohol? Any idea?
We get mixture of ketones and carboxylic acid.
They actually, the tertiary alcohol don't get oxidized, right? Because the reason is, what's the reason, Hanifa? Actually, if you look over here, you will find the reason. They don't have hydrogen, right? Here you have hydrogen, okay? And tertiary alcohol, no hydrogen is there. Is it clear?
Yes, sir.
So if there is no hydrogen, the tertiary alcohol can't get oxidized. So no oxidation. However, you should be careful if you take copper red hot tube, just note it down. Very, very important, very basic. And if you take copper red hot tube, Cu 300 degrees Celsius, you will, there is no oxidation, there is a dehydration which occurs because of the high temperature. Because H can't be removed from the carbon, there is no H in fact, so the H get removed from the carbon which is adjacent to OH. So that is actually alkene formation. But removal of water is not oxidation. Clear?
Yes, sir.
Right? So just be careful about it. Very, very important, very basic, important for all examinations. Yeah. So let me ask one question, and it's related to the alcohol chapter. There, but there are two reactions. Okay. You took the reagent P and you got X. X when you reacted with K2Cr2O7, H plus. You ended up with this compound. So what is P and what is X? Yeah, we studied while preparing alcohols. What is P? Yeah, tell me.
Is H2O.
H2O is that simple addition of water. Is it simple addition of water? Simple H2O actually not going to add because water is neutral. You don't have sufficient amount of H plus.
H2 in the presence of H2O.
H2O. Yeah, it is.
In the presence of H2SO4.
Yeah, H2SO4, but that is going to be Markovnikov addition, right? Actually, think backward. Very basic question. Where you want your OH, and think in a way that wherever you want your OH, so that mode of addition is actually, and this is the alkene which you are having. So if you want to get that OH, whether this the alkene is it, you need to do the Markovnikov or anti-Markovnikov addition to get that OH. So where the OH should be, because this is oxidation. So your OH should be at this place only, okay? Where you have the double bond O. So this is where the OH should be. And from now the whole things come. So this is X. And now you need to tell me that what is the reagent P? Yeah. This is anti-Markovnikov addition of water. Very, very important. The one method we have seen in this chapter only. Hanifa, Samaira, tell me quickly. Yeah, anti-Markovnikov addition. Actually, we use that hydroboration oxidation. I told you. Remember it from the name of the movie channel, HBO. What was hydroboration oxidation? Yeah. Any idea, Samara? Hanifa, remember what was hydroboration and oxidation? So that's the abbreviated name which I gave, right? Hydroboration, oxidation, you take BH3 and you react with NaOH group. I hope you can recall it. Right?
Yes.
So just remember it because this is very important. Now next we move to the preparation of ether and the preparation of alcohol and the reactions of ethers. That is breaking of ether by using HI. Okay, why HI is used? HI is actually a strong acid, so HI is the most famous for breaking ethers. Okay. So HI is used and HBr, HCl. Yeah, they can also be used, but HI is the most common. So that is cleavage of ethers using HI, right? So first of all, tell me, let's go for a very simple ether. This is which ether? With oxymethane. What you are going to get if you took 1 mole of HI and if you took 2 moles of HI. Yeah, very basic. Just try it, but very important. Yeah, 1 mole of HI and 2 mole of HI. What the products which you are going to get? Yes, Samira, tell me quickly.
We are going to get CH3I plus CH3OH.
Now just break it like this, okay? H and I, okay? It is going to be CH3OH and CH3I. Yeah, right. And what about the second one?
2 CH3I plus
Yeah, yeah. Actually, when you took 2 mole, Hanifa, the alcohol is going to react again with CH3I, so you are going to get CH3I and CH3I. So you are going to end up with 2 moles of CH3, right? So this is a very, very important thing. But always, this thing is going to happen. So tell me, what about this one? Yeah, yes, Amira. This is what is the common name of this ether? Very simple. Yeah, it is methoxybenzene or anisole, right? So what are the products, Hanifa, when you react this anisole with HI, 1 mole and HI 2 mole? Yeah, just tell me quickly. This is the basic, very, very basic, very important question which you need to know. Yeah, the question is same as that of the one which we discussed for CST, but there is a bit of difference in this. Yeah. So what that difference is, tell me quickly. Small thing you need to remember. In fact, I think you know, just you need to recall it in your mind.
It will be PHOH and
Yeah.
CSTI.
In the first one, PHOH and CH3. Yeah. And what about the second one? And what about the second one? If you took 2 moles.
PHI
Yeah.
and
CH3. That's what we did. But here there is a slight change. Actually, you need to know that this bond is not going to break. Okay. Why? What's so special about it? And why it's not going to break? Yes, Samira, tell me. Hanifa. Yeah, Hanifa. What's so special about it? So answer is going to remain same. PHOH and CH3I. Samira, could you recall why it has happened? Yeah. What's the reason?
maybe it is difficult to break.
Yeah, it
Or
is the way break. That's true. Why?
because it gets stabilized through resonance.
Yeah, yeah. And this pH and O bond has acquired partial double bond character due to resonance. Okay. So whatever we discussed. So remember when we discussed when we were preparing alkyl halide from alcohol, we prepared them from red phosphorus plus Br2. We used SOCl2. Okay, all those methods could be employed only to aliphatic alcohols. Okay, but not to aromatic alcohol, not to phenol, because phenol will not get cleaved. Okay, so how this cleavage occurs, just you can see over here is that you have two alkyl group. The HI actually gives H plus, and that protonates oxygen, and I minus will attack on the smaller alkyl group in this case, because it is not going to form a cation. So smaller alkyl group will be attacked. So CH3. Is it clear? Right? Hanifa, Samira, any doubts in this?
So can you please repeat?
Yeah, actually, first of all, there is a protonation of ether which happens. The H plus comes and join on the lone pair of the oxygen. Okay. And now tell me, will they break on their own? Like this one, not this one. Is it going to happen? On its own, is the cation going to form? Is the cation stable on any one of them? Are they tertiary?
No.
No. So they don't break on their own. I minus comes and pushes away one of the groups. So where I minus comes and joins it. Where I minus, so wherever there is less steric invariance, that's the position where I minus comes and attack. That is on the methyl group. Is it clear, Samaira, Hanifa?
Yes.
Okay, so that's where that is SN2. Okay, but always, so you will have CH3I and ethanol, but always this is not going to happen. You can have it in the reverse manner also, right? So how it is going to happen in the reverse manner? So here also the OH got protonated, O got protonated, but in this case the cation formed very easily. And where it formed?
On the tertiary carbon.
Yeah. So tertiary carbonate. So the other group departed with oxygen and formed, and the I minus attacked on the tertiary carbon.
So why on tertiary?
Actually, suppose if the alkyl group can break away and form a stable carbocation, then it will. So tertiary carbocations are more stable, that you know. What's
Yes.
the reason? So if this is tertiary, so the cation got the opportunity to form. Okay, but there it was not forming on its own. So I minus came and pushed away. And that was SN2 and this is SN. Getting it?
Yes, sir.
Right? Hanifa, I hope you are getting it. So this is the thing which is happening. So let's do some problems. Some very famous problems. Yeah. What's going to be the answer to this one?
Option B.
Option B. HI. Okay, one thing is for sure. So the following ether, when treated with HI, it forms what? Option B. So first of all, you need to do this, right? That's a very important thing. Then you need to think that is it going to break on its own or you are going to break it? Okay. So first of all, never break this bond because that's now we discussed. Okay. That the phenol is not going to break. Okay, because that OH is having the double bond character. So keep it intact. So this is going to be the answer. The OH is going to come with the benzene ring directly, right? Is it clear, Sumaira? This bond is not going to cleave under any circumstances. Okay.
So, but where did that other benzene ring go?
Yeah, that has formed this. So that has formed I. So this is more than one correct option. CH2I and this. Okay.
Okay.
So this is one set of products and this is another set of products, which is completely wrong because actually you broke. So try to look, don't try to look at this position. So here you don't have to break this bond because that O is actually in resonance with the benzene. So it's not going to break. Is it clear?
Yes, sir.
Okay, good. So a lot of questions are there on ethers. Same concept, but the questions are there from the mains and JEE. But this is a very important topic for NCRT also. You can use it. For NEET also a very common topic. Same. Yeah. So same thing you are going to look again, right? The thing which I told you just now. So which bond is going to break and which is not going to break? There are two bonds. So one is with the upper oxygen and one is with the lower oxygen with the so on the benzene side. Clear?
So option B.
Option A.
No, D.
Option D. Yeah, absolutely right answer. Good. Because this is not going to break anyway. Okay. So keep the OH intact over here. And in this case, break this bond because the cation can form very easily. Right?
Yes, sir.
Yeah. And this one. So if you have oxygen connected to benzene, the thumb rule is don't break it. But if you have oxygen connected to a carbon which is connected to benzene, then break it. Okay. Yeah. So what's about this one?
Option D.
Option D. Right. Correct. So got the idea how we are going to work on these problems. Right.
Yes, sir.
So this is difficult problem, but you can do it. This is from advanced, but the concept is same for NEET also. So if I replace, this is an ether, okay, with 3 benzene ring, and they have just asked, so not only related to ether, it's related to SMN. They have just asked where the rate is going to increase when the rate is going to increase of this breaking. Actually, this comes out and there is a carbocation that we know. Okay, tertiary, if you have a tertiary alkyl group, we know that there is a carbocation. Okay, so where the rate is going to increase more, where it is going to be fastest. If you replace the benzene by methyl, if you replace the benzene by paramethoxybenzene, this one. Yeah. So you need to think that the cation should become more and more stable, right? Right, Samara?
Yes, sir.
And when it can become more stable. with the benzene, already you have 3 benzene rings. Okay. The cation is going to undergo resonance. So where it is going to become more stable. Yeah.
So don't know.
Yeah, suppose if you have this para-methoxy group, then it is going to be very stable. Okay. Because that O group is OCC group is going to do more resonance. It is going to give over its electron and it's going to make it more stable, right? So if the 2 phenyl and when you have maximum are replaced by 2 para-methoxy group, so that's the place where the cation is going to become maximum stable, right? Clear?
Yes, sir.
Understood? That's the concept. Okay. But if you have some NO2 group in place of methoxy, that is actually that is against the thing. Okay, that is against the estimate. Is it clear?
Yes, sir.
Okay. So this was also haloform you did in your Learnivio. Is it covered now? I think you will be covering it
Again?
in aldehyde ketone haloform reaction.
No,
Will be covered in. Have you studied haloform?
no, sir.
Okay, that will be covered in aldehyde ketone. Right, no problem. So actually, we can start with aldehyde ketone, right?
No, sir. Actually, I guess we should start with electrochemistry.
Shall we start with electrochemistry?
Yeah, sir.
Yeah. Okay. So just a second. So in electro, actually, just today we can have some introduction and we can have. So in CBSE also electro is started. So basic cell representation, are you aware?
Yes, sir.
So tell me what's the standard EMF, what's the electrode potential is actually on which factors the electrode potential depends. What are the factors which govern electrode potential? Yeah. So suppose if you have a copper rod dipped in copper solution, copper sulfate, right? Okay. What are the factors on which the electrode potential will depend? So what's the so how many types of electrode potential are we having? Yeah. Reduction and oxidation. What's the difference?
In oxidation, there is removal of 2 electrons, and in reduction, addition of 2 electrons.
Yeah, it is the measure of tendency, right? Cu2 plus. So this is what? So which one is which representation?
First one is reduction, and the second is oxidation.
Yeah, SRP. Okay, it not represent the standard reduction potential. Now, what that value is, if you are aware? Yeah.
0.34.
Yeah, it's 0.34 volt. Correct. And what's going to be the electrode potential for this one?
Minus 0.34.
Yeah, it's just the reverse. Okay. So this is standard electrode potential, and how do you measure it? That you know. How do you measure it? Tell me quickly. How? What's the reference for measurement of this standard electrode potential? Yes, Amara. So how do you experimentally measure? You measure using it with which one? Which standard hydrogen electrode? Okay. So that is the you compare it with standard hydrogen electrode, and what's the electrode potential of standard hydrogen electrode? That is a reference electrode. All the half electrodes are compared by connecting them to standard hydrogen electrode. And what's the equation? What's the representation of standard hydrogen electrode? Okay, that is 0 volt, right? That you know. Okay, any doubts on this? The basic thing you know, right?
Yes, sir.
Yeah. So let's move to the question.
So I'm confused about that signs. That why 0.34 is getting minus sign.
Yeah, okay, what you do, let me make you understand. Very simple it is. Suppose each metal has its tendency to either gain or lose electrons. Okay, so copper rod, when you dip it in copper sulfate solution, it will, so two things can happen. Either the copper atoms on the rod can give away two of their electrons to the rod, and the copper ions will get into the solution, aqueous solution. Okay, under that it is going to become negative charge. Okay, the rod, the current is not flowing. That is going to acquire a negative charge. Okay, and it has more tendency to lose electrons if this happens. Okay, and suppose if there can be other thing which can also happen, and that is the copper ions from the solution can go and stick onto this rod by taking away electrons, free electrons on the metal. So if the copper ions get stuck to these copper rod, the rod will become positive, and in this it is gaining electrons. Okay, it will acquire a positive charge. So when that electrode is isolated, it is not in contact with any. So each metal has its own tendency to gain or lose electron. But how do you measure? You can't measure it, okay, because you need the current to flow, and alone you can't measure it. So what you do, you compare it with standard hydrogen electrode. So standard hydrogen electrode is the reference electrode. Okay, for that you take the tendency, whatever. So because you need to connect to any electrode, then only you will able to start work, or able to find out whether it is giving electrons or taking electrons. Or but independently, if it is not connected, then you are not going to find able to find out. You need current to flow. That is going to tell you whether it is giving its electron or losing its electrons. Okay, so you connect it with the standard hydrogen electrode, right? So what you observe here is this is standard. So what's the characteristic of standard hydrogen electrode? How it is made? That is clear. Samira? And if the current is flowing, if the electrons are flowing from a standard hydrogen electrode to copper, what does this indicate? Yes, Samira, can you tell me? This yeah. So this indicates the copper has more tendency to accept electrons. Is it clear?
Yes, sir.
So copper has more tendency to accept electrons. So this is so actually the oxidation potential can be reduction or the electrode potential can be reduction potential or oxidation potential. You can express both of them, but IUPAC, as per IUPAC, reduction potential is the standard electrode potential which is considered. So this is the electrode potential of this is the representation of the equation of the electrode potential of standard hydrogen electrode, and that is 0 volts. Okay, you connect a meter, and if the electrons are flowing towards, when you connect each of them, each one by one, each of them you connect them by the standard hydrogen electrode, and if the electrons are going out of the standard hydrogen electrode and going towards the electrode which you have connected, that means this one has more tendency to accept electrons. Is it clear?
Yes, sir.
So if you have, so actually electrode potential is a measure of standard reduction potential is a measure of it is a measure of tendency to take or accept electrons. So for copper it is higher, so I'm going to place it above the standard hydrogen electrode, so it is going to be 0.34 volt. Clear? Right? So more higher the tendency is, higher is going to be the element which is going to placed in this. So I hope this is clear to you. Right?
Yes, sir.
And what about zinc? What is going to happen if you, what's the electrode potential of zinc?
It is 0.776 or 9.
Yeah, it's minus 0.76. It's the reduction potential. So what can be interpreted in just a simple way regarding the zinc and how it should be placed when it is connected to standard hydrogen electrode? Yeah. Where it should be placed? Should I place it on the right hand side or on the left hand side?
Left hand side.
Yeah. Why left hand side?
Because oxidation takes place.
And that is, it is having less tendency to accept electron. That's why, so it is having less tendency to accept electron as compared to standard hydrogen electrode. That's why it is minus. Is it clear?
Yes, sir.
Because zinc is electropositive, it is considered as an electropositive element metal, so it has less tendency to accept electrons. So if you give that electron, it will be minus. Means so it has, so if it has less tendency to accept electron, that is equivalent to say that it has more tendency to give loose electrons. So it will lose electrons, and as compared to standard hydrogen electrode is the reference that has neither tendency to gain or lose, but zinc has more electropositive, it has more tendency to lose electrons. So then the zinc will give, and it is going to act like an anode, and the standard hydrogen electrode is going to act like a cathode. You measure the voltage over here. Okay, EMF. So what's the formula for the EMF of a cell in terms of reduction potentials? Yeah. Remember it? Yes, Amira.
It's A.
Yeah, in terms of reduction potential, it's E cathode, E right minus E left. Okay, E cathode minus E anode. So it is, so here the voltage EMF is 0.76 volt you measured for this cell, and this is E cathode is standard hydrogen electrode. So it is assumed to be 0 minus E naught anode. Okay, so that is so you will have this value E naught anode or zinc 2 plus 2 zinc, that is going to be minus 0.76 volts. Is it clear?
Yes, sir.
So you line up all the elements. Okay, you line up all the elements like this. And in the middle you have that 0.0 volt, which is for the standard hydrogen electrode, and which is the one at the top. Yeah, yeah, which is the one at the top of this electrochemical series, or the one which is having the very high tendency to accept electrons. Yes, Amira. Remember it?
Sir, I don't remember.
Yeah, it's the fluorine F2. So it's the strongest oxidizing agent. Is it clear? The highest tendency to accept electrons. Okay. And which one is the least, which cation is having the least tendency to accept electrons? Which one is it? Yeah. It's there in your NCRT. So in CBSE, how much is covered till now? In Learnivio, tell me. Yeah, you must just revise it or let me know. And so what's going to happen here? Tell me. Yes, Amira. Which is the one? So this is the lithium. Okay. So lithium, the reduction potential is minus. So that one is having the highest value. And this lithium is going to have minus 3.04 or 3.05 volt. So it's going to have the lowest value. So lithium is the strongest addition. Means or lithium cation is actually the one which doesn't want to accept electron at all. Clear or not?
Yes, sir, clear.
So you compare. So you compare. The upper one is actually the more oxidizing, more desperate to take electron, and the lower one actually is more desperate to release electrons. So you can compare the oxidizing and reducing nature of these, right?
Yes, sir.
Clear? So there are a lot of questions which are asked. Most common questions are these only, and that is related to your electrochemical series. Okay, so let me discuss few of the questions. So I hope this is clear, concept is clear. Okay, and
Yes,
it's
sir.
very easy. You can just go through an NCRT also, and you will just be able to do it. Just quickly go through it. Okay, so I will write few values in front of you. Ag plus electron, that is going to give you Ag. Okay, and zinc 2 plus 2 electron is going to give you zinc. Copper 2 plus is going to give you copper upon accepting 2 electrons. And you have, let's say, chromium 3 plus. Okay. So standard reduction potential is going to be minus 0.74. These are electrode potentials. Okay. So now tell me, the best reducing agent. Okay. So is it the copper 2 plus or the copper or the silver, or is it the Zn?
Zinc,
Yeah, zinc is the best reducing agent. Why?
because it has the least SRP.
Yeah, the one which is having the least reduction potential, lowest reduction potential, it is going to be the most reducing one. Okay, so it's zinc. Okay. And who is the strongest oxidizing agent?
Ag,
So actually here you need to be very careful. Yeah. A, B, C, D, 4 options are there. Which one is going to be the strong? Yeah, Ag what? I'm asking which one is the strongest oxidizing agent. The oxidizing agent is the one who needs electron, who takes electron. And always this is the thing which go wrong. Yeah, tell me. You
Ag
are,
plus.
yeah, it is the Ag plus. Yeah, you need to take the, if you Ag plus, because that is the one which is going to accept electrons. Okay. Yeah, right, correct. Okay. So this is one application. So another application is, can I store zinc sulfate in copper vessel, or do I store copper sulfate in zinc vessel? Tell me. Yeah, which is correct. So both can be done.
Both can be done.
Both. Actually, you need to choose the option where there is no reaction happening. If there is a reaction happening, your vessel is going to dissolve. Okay. So you have the values in front of you, just check it. Yeah. So actually the zinc is zinc plus 2 doesn't want to take electron. You can have the value from here, right? That is clear.
Yes, sir.
So zinc doesn't want to take electrons. Okay, that is clear. And in this case, you can. So in this, suppose if the reaction happens, Cu2 plus zinc and zinc 2 plus and Cu. So in this case, what is happening is the zinc taking electron or giving electrons?
Giving electron.
Yeah, it's giving electrons. So zinc can give the electrons. It has no problem in giving because it is an electropositive element, but it can't take it. The electrode potential is negative. Okay. So actually zinc can lose electrons. So if it loses to copper, you will the vessel will dissolve. So this option is incorrect. This is correct because zinc 2 plus you have taken zinc sulfate, that is not going to take electron, and that is good. The zinc sulfate will remain zinc sulfate. But the copper sulfate, if you would have taken in zinc, zinc is more reactive, more electropositive. That is going to give electrons to the copper. Copper is going to get reduced. Okay, so this is the right option where no reaction is going to happen, and this is the incorrect option. Okay, so that you need to keep in mind. So I hope that is clear. So
Yes, sir.
let's cover it on the next turn. Okay, some more concepts of